I have a question for you. What's the difference between this device and that device? And I know, they closely resemble each other. Both of them have a screen in the center and buttons on the side, so I'll give you a moment for thinking. Alright, the answer is one has a dedicated electronic circuit that is called GPU, which complements CPU in 3D computations, while the other one has only the bare capacity to output video display. Besides, yes, one is black and the other is white. I'm asking because, as you may probably know, I'm working on a C++/OpenGL remake of a game called Spelunky Classic by DirectQ, and since the very first working version, I'm trying to cross-compile it and run on a variety of devices. So far, these devices had one thing in common. They had a GPU. It was required as I'm utilizing OpenGL as a rendering API, meaning that a great share of work could be taken off the CPU and put on a GPU through various OpenGL commands. You submit commands with vertices that you want to render, matrices describing camera transformations, textures that you want to display over the mesh, and GPU does the work on its own. But that doesn't really restrict me from running an device without a GPU, and you may be puzzled right now because you do need a GPU to display something, right? Well, not exactly, because nowadays the difference between a GPU and a video card became very thin. Video card will almost always have a GPU, but in the old days, when graphics accelerators weren't a thing or were just something new, you could have a video card that was purely for generating electric signal that your display could understand without a GPU. Even now, many embedded devices do have a capacity to output video, but don't have a GPU. PocketGo is such an example. So we can have a video card without a graphic acceleration. Having graphic acceleration on the other side has obvious benefits. It will do certain types of things much faster than a CPU, particularly when it comes to specialized SIMD programs, when there is multiple data and a single instruction. And also, during time saved because of GPU, CPU can do other things for which it is better suited as a general-purpose device, for example, detecting collisions in the game, calculating physics, handling network connections. As you can imagine, putting all those responsibilities on a CPU means smaller frame rate, because there's so much to be done in between the frames, and also frame rendering itself takes time. But I did it. I ran SpelunkyPSP on PocketGo without a GPU, and spoiler alert, it wasn't playable. Before any practical showcases, I wanted to present some historical context, because I think you can't really grasp the topic without knowing the historical context behind it. And the history of display on Linux starts long before Linux itself. It starts in the early 1980s, when multiple competing video card standards are created. There's HGC standard by Hercules, there is CGA standard by IBM, it is later superseded by EGA, and since 1987, the most important from today's perspective, VGA standard. VGA standard became very widely adopted, both within software and hardware manufacturers. It's even used to this day with some additions built on top of it, so it's not surprising that when a few years later some dude called Linus Torvalds came up with Linux, early kernel distributions utilized VGA in text mode as the console video output. Here's the Linux Journal, issue number 8 from December 1994. In the section about writing kernel drivers, there is written, quote, "While the Linux startup code has options to initialize the video modes for many different kinds of cards, the actual device support for video cards in the Linux kernel proper is extremely limited and is comprised of support for putting text on the screen on either monochrome, Hercules style, or color CGA, EGA, VGA and above cards. No support for graphics is included." So the early Linux kernel did not provide anything video card related besides the bare minimum for displaying console. Using VGA to display text on the screen is even to this day taught in OS development tutorials. It is the most basic and universal thing that you can use to put something on the screen. The working principles are to memory map some address space to video card's memory, so upon writing to it, CPU would write to the video card instead. The rest is just to poke some addresses the VGA specification says to poke. Naturally, some utilities were created like svglib, so to ease display access and to do the low-level things behind the curtains. Here is the Linux Journal, issue 66 from October 1999, which besides such articles like Java version 2 software development kit, features a section called Stupid Programming Tricks. And to quote, "Many people are bored with the console. It's just text. Console games are stupid," they often announce. However, many games are available for Linux which take advantage of console graphics. They use the entire screen, don't require X, and don't have solid borders and buttons all around them. Console graphics are fun, fast, and much easier than graphics in X. The established Linux console graphics library is svglib with its sidekick VGA-GL. svglib is a low-level graphics library and VGA-GL is fast Framebuffer-level graphics library for use with svglib, containing many drawing, text, bitmap, screen buffering, palette handling, and 3D functions. Using these two libraries in conjunction makes programming graphics for Linux exceedingly easy, and both are included in practically all Linux distributions. Although svglib doesn't work on some cards, needs root privileges to run, and may require an immediate reboot or even crash the machine if things go wrong, it usually works and lets us do much more than X. That part about crashing the computer sounds really worrying, but nevertheless, VGA is, in the end of the day, only a mean of video output, and if you can blink a few pixels with it, you could render a whole 3D scene into RAM and blink it on the screen as well. Issue 57 from January 1999 features instructions on how to run Quake with svglib, so you see it was really popular these days. But let's get back to the article before. As you see, there was some problem, there was a limitation in applications using video card in this direct way. Good luck running more than one application that does it this way. Good luck recovering from an application that crashed and left it in some unknown state. No, you need some kind of an arbiter, some central authority that will manage which process is drawing right now, that will know the current display mode, the current resolution, the current refresh rate. That central authority came, and it wasn't in the kernel yet. It was in form of X Windows Server implementation called X386, initially released in 1992, a thing that later became Xorg. I'll just refer to it as the X, and by which I mean this particular implementation. Since then, your application contacted the X server running on your computer to draw something, instead of poking some addresses like some unmarried child. X server was the only process having exclusive right to the graphics hardware, and that allowed having multiple applications drawing to the same screen at the same time, since X server was synchronizing them. It doesn't mean that everyone instantly moved to the X server. There were still people who preferred svglib, and that's understandable, as it has some upsides to it. To quote svglib tutorials, how is svglib different from the X Windows system? The X Windows system, X386, is actually a server. This server must be started prior to using any applications which require X. Furthermore, the X server is unabashedly system intensive. In example, it's piggy with your resources, and when using some video cards, it will prohibit you from using your virtual terminals. svglib, on the other hand, requires no such preparation. You do not run svglib like you do X Windows. svglib is simply a binary C library, which is called by C programs, just like all the other libraries in /lib and /user/lib. But back to the X. Xserver became the standard display stack on Linux, with some video card drivers being implemented in its codebase. You wanted your application to utilize hardware-accelerated OpenGL? Well, you better utilize Xserver API for OpenGL, GLX, because it's the Xserver that implements the drivers. It's the Xserver that knows how to talk to your GPU. And besides, it already has an exclusive access to it. This way of rendering, where your application doesn't access hardware directly but rather has a middleman in between, in example in form of the Xserver, has a name and it's called indirect rendering. You probably see an issue, right? This way, loads of display-related utilities were centered around the X, not around the kernel, making you dependent on the X, regardless of your needs, regardless of the device you're developing on, either mobile or desktop or embedded. You had to have it to utilize hardware acceleration. And besides, modern 3D applications tend to issue loads of OpenGL commands. So by having a middleman in between your application and the hardware, you're wasting loads of CPU cycles on this communication. And even on top of that, there was a security issue, because the Xserver accessed hardware directly, it had to be run as root, and that made it an obvious target for hacker attacks. Remember when I said that initially the Linux kernel provided only the bare minimum for displaying text? So it was, until 1996, when Linux kernel 2.1 rolled out introducing the Framebuffer device concept. And if there's one single most important thing from this chapter of the video, it's the Framebuffer device. It was the first step done to move some responsibilities off the Xserver to the kernel space, as now the kernel was the central authority for display hardware. Now you could display things without the X, although with no hardware acceleration, as the GPU drivers were still tangled with the X. As an example, here I'm using the Framebuffer device to display SpelunkyPSP on the Raspberry Pi 3 using Adafruit display. The kernel driver for the LCD controller is loaded and exposes a special file /dev/fb1 to which I'm writing pixels. More on using the Framebuffer device in the later section of the video. Today there are multiple frameworks that support direct usage of the Framebuffer device, in example SDL, Qt, or a more specialized DirectFB. The most common case for using the Framebuffer device is embedded devices, where resources are scarce and you just don't want an overhead of hosting the Xserver. For the sake of having a complete picture of the Framebuffer device, I'll also read an article from issue 60 from April 1999 of the Linux Journal. Part 1. What we have today. Text mode, Linux's most basic output method, is also one area where Linux has changed little since the old days. The text mode console of Linux 2.0 is pure in its simplicity, with one obvious and maybe striking fact: no code for graphical primitives is in the kernel. The lowest level interface to the text mode kernel is as simple as the file stream. Higher level functions, such as would be required for full-screen text console applications, are done through a superset of VT100 terminal protocol. Libraries such as ncurses are built on top of this to simplify programming and to provide a sort of terminal abstraction. Applications written for Linux's text mode using this abstraction can run on just about any terminal. SvGLib. There's obviously quite a bit more to modern hardware than simple text modes. As mentioned before, kernel hooks are not provided for accessing these functions, but many user space programs and libraries are available that bypass the kernel altogether to access the hardware beneath. Unfortunately for SvGLib, the most popular alternative, the support API provided is heavily tied to the features of the VGA hardware, making it difficult to port either the SVGA library or the end application to any other type of hardware. Limitations aside, SvGLib has proven to be a stable and popular solution to the console problem and is the primary interface used in Quake and other games. The X window system. The final and most popular option for accessing the video hardware under Linux is through the X window system, the most common GUI subsystem for Unix. The X Windows system includes an X server, which is similar in purpose to a Windows-style video driver. In addition to driver features, the X server includes code for running programs over a network and handling many GUI tasks internally. In this respect, the driver portion is not truly separate from the server portion. A program that wishes to access the video hardware would do so by communicating with the X server through its API. Because of the combined driver/server features of the X system, servers tend to be very large, making it difficult to allow programs to run in low memory situations. Framebuffers. Framebuffer devices are the biggest new feature of the Linux 2.2. Unlike earlier versions of Linux, it is possible through the Framebuffer device to access the video hardware of a machine directly and in a device-independent manner. All the basic graphics primitives are supported, although acceleration is not generally supported at this time. In addition to these features, it is now possible to access the Framebuffer devices through the use of device nodes, just like any other device. As an example, these devices /dev/fd can be used to get a screen capture simply by doing a standard copy command. Above the Framebuffer is the Framebuffer console, fbcon. Now, all of these features are great, but the major feature that will probably be the reason most Linux users try out the Framebuffer driver is the boot logo. Yes, now we can finally have a cute little picture of Tux carrying a beer whenever you turn on your computer. Part 3. Advantages of the Framebuffer. My favorite feature of the new kernel subsystem, if it were to go into ideas, can be summed up into words: cross-platform compatibility. Simply put, applications written to use the Framebuffer will be immediately portable to all Linux platforms. This is in direct contrast to the current SVG-lib system, which does have some cross-platform compatibility, but only on systems with VGA-like hardware. This will, in theory, make compiling any graphical application on multiple Linux architectures as easy as compiling an application with ncurses is today. The final piece of the puzzle is the DRI, introduced in 1998. Some GPU communication-related parts were moved out of the X to create a separate framework out of it. From what I understand, DRI exists to have a generic way of implementing GPU drivers. In example, Mesa utilizes it this way. On the kernel space, DRM was introduced to synchronize all parties trying to access GPU through the DRI. Again, some responsibilities were moved out of the X to the kernel space. With successive versions of the DRI, even hardware acceleration became possible without the X, as accessing GPU moved to the kernel altogether. Finally, direct rendering became possible. Knowing all this historical context, I want to fast forward to 2020 to cover the current architecture of accessing hardware acceleration. I'll help myself with this diagram and follow the path of a hypothetical 3D computer game from the topmost layer to the bottommost layer, which is the hardware. So let's say we have this 3D computer game. It says a 3D computer game, but it can be any application that uses GPU. As a matter of fact, there are applications that don't even display anything, but use hardware acceleration. For example, there is Hashcat, which is an application for calculating hashes, and it doesn't even display anything. It's a command line application, but it can use GPU to make things faster. It doesn't even open any window. It doesn't even capture any mouse or keyboard events, so this block can be completely removed. So we have this generic 3D application, let's say, that links to Mesa. Mesa is this GPU driver vendor that implements a variety of drivers. So our application links to Mesa, and it does all the OpenGL calls through the Mesa. Mesa, which implements the actual driver for the underlying GPU card, does the communication with the kernel. The kernel has the DRM module. The DRM module does the synchronization between a variety of parties that may try to access the GPU at the same time. So MESA communicates with the DRM, which makes the actual communication with the GPU. Now, this diagram makes an important assumption, that you do have a GPU, which is not the case on PocketGo, obviously. So later I'll show you a slightly different diagram, which is a modified version of this diagram made by myself. Here's a terminal session being displayed on the Framebuffer device through the FBCon. Let's toy with the Framebuffer to get a more practical overview, because understanding Framebuffer devices will be crucial to run SpelunkyPSP on PocketGo, since, as it happens, PocketGo is a Linux-based device and has kernel drivers exposing a Framebuffer device. The Framebuffer device, as other devices on Linux, is a file. Let's see if this system has a Framebuffer device or devices, because there could be more than one. It appears that there's a single Framebuffer with an index of 0. You can write and read from the Framebuffer like from any other file. As an example, I will direct other Linux device dev-urandom, which outputs random numbers, into dev-fb0. As expected, random pixels appeared on the screen upon writing to the Framebuffer device. The same screen that is used to output console contents. Question is, why did it happen? Framebuffer is an abstraction for video card memory. Imagine it as a 2D array of pixels that is somehow wired to the display. Whatever you write to it will be shown on the screen, with kernel drivers doing the job behind the curtains. Let's do the very same thing on PocketGo, as it is also a Linux device. The screen blinked. That's because Framebuffer content was changed, but the console emulator that is also running on the Framebuffer overwrote it almost instantly with text. But the point is, this is portable across Linux-based systems. Now that we know how to display random pixels over the screen, we'll have a walk through a very short C program that utilizes Framebuffer and displays something more predictable. The program starts with opening the Framebuffer device file, and if everything went successfully, it gets the screen information, for example, vertical and horizontal resolution and bits per pixels. Again, if everything went successfully, it memory maps the Framebuffer device file, so everything you write into this Framebuffer pointer is actually written into the device. If everything went successfully, it sets half of the Framebuffer into FF in hex, which is white, and the other half is set into 33 in hex, which is some shade of gray. Then the cleanup is done. Let's compile the file and run it. As you can imagine, if Framebuffer gives you that much of control, it could display an image as well, right? And that's correct. So if you can display an image, you can probably display a video too, right? And that's correct. But the question of running OpenGL without a GPU is still unanswered, and it's time for the diagram that I promised before. As I said, this is the diagram that I shown before, but with my own additions on top of it, so please take it with a grain of salt. That being said, what blocks are missing? The most obvious one is the GPU missing in the hardware layer. On the kernel layer, there is no DRM driver. There's no DRM driver because, as you may remember, DRM is used to do the actual communication with the GPU. So if there's no GPU, there's no DRM needed. If there's no DRM driver, there will be no DRM communication library on the user space side. So starting with your game links to the software OpenGL implementation. It may be Mesa, because Mesa provides software fallback, but it could be SwiftShader or TinyGL. It sends OpenGL commands, and the OpenGL commands are done on a CPU. Your library does it, not the GPU. They are not passed down, they are done in this block specifically. So they are rendered into some memory buffer, or they are rendered into the Framebuffer device directly. An example, Mesa provides a library, GL-FBDEV, that will render directly to the Framebuffer device, and once you write to the Framebuffer device, the driver will do actual display. It will send the contents to the display controller. But it could be TinyGL, for example. TinyGL renders into a memory buffer that your application has to copy to the Framebuffer device, so this path would be taken. But either way, the philosophy is like this. You render into a memory buffer and you send to the Framebuffer. No GPU is involved. And that's it. That's how simple it is, at least how I imagine this. There are 3 software OpenGL vendors that I listed, and there may be more, but it's these 3 that I want to cover. There's Mesa, which as of today implements highly accelerated OpenGL for various GPUs, but still it delivers a software fallback. Historically, it began as a project with only OpenGL software implementation. The most recent version does not support rendering directly into the Framebuffer device, but there are legacy versions that do support it, and I'll cover this later. There's also TinyGL, which, as the name suggests, implements only a small subset of the OpenGL 1.0 standard, so it's not even a complete OpenGL implementation, but because it's small and very straightforward to integrate, I think it should be mentioned. It doesn't support rendering directly into the Framebuffer, it renders into a memory buffer, which your application has to copy into the Framebuffer to display it. However, there are forks which already do it. An example, TinySDGL, which uses SDL to copy the contents of the memory buffer into the Framebuffer. The last one, SwiftShader, originally made by Google to bundle it with Chrome and have software OpenGL fallback on platforms without GPU or GPU drivers. But it doesn't only ship software OpenGL implementation, it does ship Vulkan implementation too. It supports Windows, Linux, OS X and Android. Having all of them briefly covered, I'll use Mesa with its GL-FBDEV library to finally run SpelunkyPSP on PocketGo. And why not the others? Well, honestly, I tried to cross-compile SwiftShader to PocketGo and I failed. I think it's just not meant to be run on embedded platforms, but who knows, maybe with some tinkering with the toolchain I could finally build it. I don't know. TinyGL, as the name suggests, it implements only a small subset, too small. Some symbols that I utilize in SpelunkyPSP were missing, so again, I couldn't even build SpelunkyPSP with it. And Mesa with its GL-FBDEV, on the other hand, it built and integrated almost without any problems. Alright, so I cloned Mesa. I checked out this specific version, 7.9.2, which is the last version that ships GL-FBDEV library. It's quite old, it's from 2011. The most recent version is, I think, 20.2. So, on top of that, I made some additions. I removed a flag here and there. I don't build targets that I know that I won't need. I typed paths to my compiler and linker here because I just don't want to edit my environment every time I build it. And yeah, that's about it. Let's call make. It will take some time. And that's it. Let's see the artifacts. A brief introduction to SpelunkyPSP build system. So there is this source directory in which I define multiple CMake targets, each in its own directory. For example, there's this audio target, there's this camera target, there's this collision target, and each of those targets exposes an interface in form of header files. So there's this clean cut, so to not tangle the code together. What's most important, there is this video target. Video target is special because it has a lot of conditional branching depending on the platform it is targeting. Because I just don't want to litter my code with if-defs and other preprocessor directives, I do a clean cut through including separate files, separate implementation files depending on the platform. So there is this video PSP, video desktop, video Android, and they are included depending on the platform that is targeted. Let's see the interface of the video module. There's this setupGL method, and that's the most important method of the video target. What setupGL does is it creates OpenGL context. OpenGL context is just an OpenGL setup that you need to do on each platform before you call OpenGL functions. So let's visit setupGL implementation of the video desktop CPP. This implementation is utilized on generic Linux and generic Windows targets. So I call SDL, usual SDL boilerplate, and after that I initialize SDL with SDL OpenGL flag. So that should give me OpenGL context if it's supported on this platform. What I do later is I call GLAD. If you don't know GLAD, what GLAD is doing is it delivers OpenGL headers for a specific version that you need. You don't want to tangle your code with system headers because they tend to differ, and the best solution if you're doing an OpenGL project is to just create headers for the version you are targeting, which is 1.0 ES in my case on mobiles and 1.3 on desktop, and bundle those headers in your code base. What is done specifically here is it loads the actual pointers to the functions from the headers. So this is done in runtime, and it may fail if the platform doesn't really support OpenGL with these versions or OpenGL at all. So may compile, but it may fail in runtime. What is done later is, again, some GL boilerplate. I'm disabling functionalities that I know that I won't use. How it's done on PSP? It's very similar. It's using SDL 1.2 with some minor differences. There's resolution hard-coded here, while on desktop it's using full screen. On Android, however, it's utilizing SDL 2.0. Why SDL 2.0? Because it supports Android from this version on. Why am I talking about the video target? Because what will need to be done to support PocketGo is to create another video file, video_PocketGo or something like this, and in it implement setupGL method. Alright, so there's this GL-FBDEV test.c which method delivers, and it is an example of creating OpenGL context with GL-FBDEV. And as you see, it's very, very, very verbose. You have to do lots of things to create OpenGL context with GL-FBDEV. There's a lot of comments and branching depending on the screen resolution and bits per pixel. I could remove lots of this because I know the screen specifications on PocketGo, but nevertheless, it's loads of things. So what I did was just copy-pasting the parts of creating OpenGL context into SpelunkyPSP, into the new file video PocketGo. Here's the video PocketGo implementation file. As you see, there's this boilerplate that I copied from the example shown before, but in the end of the day, there's still this setupGL method implemented. So to create OpenGL context, I'm calling initialize-FBDEV, which is just calling the boilerplate above, and eventually I'm calling glad. In this case, I'm passing GL-FBDEV getProc_address function pointer. On desktop, it was SDL GL getProc_address. So glad takes function pointers from different vendor. After that, almost the same boilerplate as in the case of desktop or PSP or Android. Besides the setupGL method, there are other methods that are platform dependent, for example swap buffers. Swap buffers on PocketGo delegates to GL-FBDEV swap buffers, while on desktop it is SDL GL swap buffers. That's the only differences that I had to apply to make it work on PocketGo. That's the only differences that I had to make it work with GL-FBDEV, because it doesn't necessarily have to be run on PocketGo. And that's it. All those changes are encapsulated within the video module. Now I'll finally do the cross-compilation to the PocketGo. Let's call cmake with the toolchain file for PocketGo, and let's call build with all threads. It will take a moment or two, and that's it. It compiled and linked. Let's check the file. It says it's 32-bit ARM, and that's fine. So now I have PocketGo SD card connected to the computer, so I'll do the copy command. That's it. And also, I need to copy the runtime libraries, the artifacts of Mesa that were built. So again, let's do some copying. Let's start from finding all the runtime libraries. That's it. So now let's issue the copy command. And that's it. Once it's done, I'll eject the SD card and plug it into PocketGo. Let's run the terminal and get to the directory with SpelunkyPSP. Now, because I copied all those Mesa runtime libraries, they should be present here, and they are indeed. So now let's run SpelunkyPSP, but we'll modify the LD library path, so the system, the linker, would prefer those libraries instead of those that may be installed in the system with the same name. Okay, let's run it. And it is. Software implemented OpenGL on PocketGo. Problem is, it takes around 700 milliseconds to render a single frame, which is around 1.3 frames per second, which is literally not playable. Now, for the sake of curiosity, I rebuilt the game so it would add less render entities to the loop. And it actually gets pretty decent FPS, but you can't say it's playable this way. Running SpelunkyPSP on PocketGo made me realize two things. Firstly, forcing an application to use software-implemented OpenGL may be as simple as dropping the GL library into the path, so the application would link to it in runtime. And that makes me wonder how many computer game hacks were done exploiting this simple fact. Because imagine that you had some very custom build of Swift shader that printed all the shaders that the application sent to it, and you identified the one shader that is used for rendering enemies, and you changed it. You changed it so the enemies would be more visible, in example colored in a very bright color, and that's it. You have a very simple computer game hack. And secondly, after all, setting up a software rendering without X, without GPU is quite simple, but rendering even simple quads on a hardware-constrained platform like PocketGo is not worth it. It won't fit to the task because it's very CPU expensive. And yes, there's a number of potential optimizations that I could apply on my code base. I could apply greedy meshing, so to decrease number of vertices in the tile map. I could make the resolution of textures smaller, which is a funny idea because those are pixel art already. I could apply spatial partitioning with frustum calling, meaning that I could split the tile map into smaller chunks, and depending on whether those chunks are in the camera frustum, I could render them or not. I could make the camera frustum smaller because the smaller the frustum, the less things on the screen, the better the frame rate. But the ultimate optimization I could apply is to just not use OpenGL at all for simple 2D graphics. OpenGL adds just too much overhead to run it on such a constrained device. To render a simple textured quad, you have to provide vertices, indices, matrices, UVs, while frameworks such as SDL provide API for 2D primitives without that much of abstraction. And SDL supports Framebuffer devices out of the box. So will I rewrite the renderer? Not before I actually finish writing the game.